Hello! Today we will learn about the color code of carbon resistors. A color code is used to indicate the resistance value of a carbon resistor and its percentage accuracy. There are two systems of making the color code, and the color code used throughout the world is shown in this table. Let's discuss first system of color code. In this system, you have to note the first two rings from the end give the first two significant figures A and B of resistance in ohm, and the third ring indicates the decimal multiplier. Firstly, you have to note the rings of first two color from the end, and then see from the table. In this table there are black, brown, red, orange, yellow, green, blue, violet, grey and white, and the letters are written, and for each color there is a number, and for the color gold, silver and no color the tolerance is given to you. You can remember this table by using this line that B.B. Roy of Great Britain has very good wife. Here B stands for black, next B stands for brown and so on. Now let's understand this system by taking the first figure. Here the colors are brown, violet and blue and the gold. So first color is brown. That means from the table brown means the number 1. So instead of A, the first significant figure, you have to write 1. Then V stands for violet. For violet you can see that the number is 7. So the next significant figure is 7. So you got the number 17. And the third color is black, and for black the number is 0. That means 10 raised to the power 0. So you got 17 into 10 raised to power 0, and you can see that the next band is of gold. So from the table gold means 5% tolerance. So it is 17 plus minus 5% ohm. Let's consider the next figure. In this, see, on one end there is silver, so you have to take the color from the other end, and the first color is green, then red. For green you know that the number is 5. For red it is 2, so you will write 5 2. That means 52 multiplied by 10 raised to power the number of the third band color, and the third band color is blue, so you got 52 into 10 raised to power 6, and as silver has a tolerance of 10%, so you got 52 into 10 raised to power 6 plus minus 10% ohm. The second system of color coding of carbon resistors, see the figure here. In this, the body is of yellow color, the ends are of red color, and there is a dot on the body, and that dot is of blue color. So, and there is a band either of gold, silver, or there may be no band on it. So what are the steps? Firstly, you have to note down the color of the body, and that will give you the first significant figure. Then you have to note down the end color, that will give you the second significant figure. And then 10 raised to the power, the significant figure comes from the dot end, right? And the color of the ring give you the tolerance. So let's find this. you can see that it is a yellow body, the red ends, the blue dot and the gold ring. So from the table, find out the numbers and you will get what? For yellow 4, red 2 multiplied by 10 is to power blue number 6, and for gold it is plus minus 10 is to the power 5 ohm. Now you know that metals have a large number of free electrons, and in the absence of any electric field, these electrons are in a state of continuous random motion due to thermal energy. And at room temperature, they move with velocities of the order of nearly 10 is to power 5 meter per second. However, these velocities are distributed randomly in all directions, and on the average, the number of electrons traveling in any direction will be equal to number of electrons traveling in the opposite direction. And if u1, u2, u3, un be the random velocities, then the average velocity will be 0. That means there is no net flow of charge in any direction. And in the presence of an external electric field E, each electron experiences a force of E into capital E in the opposite direction to the external field capital E, because the electron has negative charge and undergoes an acceleration, and you know that acceleration is equals to force upon mass. So the acceleration will be minus small e, the charge on electron, into capital E, the external electric field, divided by the mass of the electron. Since the electron is accelerated for an average time interval tau, so the additional velocity acquired by the electron will be equals to Vd equals to A into tau. By putting the value of A, E by m into tau, and if we take the vector sign, then the Vd vector will be equals to minus of E into capital E vector upon m into tau. And this Vd, the small velocity imposed on the random motion of electrons in a conductor on the application of electric field, is known as drift velocity. In the figure, consider a conducting wire of length L and having uniform cross-section area A, in which there are n free electrons per unit volume, means small n represents the number of free electrons upon the volume, and they are moving with drift velocity Vd. Now, in the time interval delta t, each electron moves a distance, you know that, speed into time, so Vd into delta t, and the volume will be equals to area into the distance, so A into Vd into delta t, and the number of free electrons in this portion will be number density into volume, so you got n, small n, into A Vd delta t, and all these electrons crosses the area in time delta t, and therefore by using the formula charge equals to Ne, so you got number of electrons NeAVd into delta t, or you can say that you know that current is equals to charge upon time, so you got NeAVd delta t upon delta t, so you got simply NeAVd. This is the very important relation between the current and drift velocity. So remember, I is equals to NeAVd, and take care that their small n represents the number density, means number of free electrons upon the volume. Now, In terms of current density, you know current density is equals to current upon area. So you got J is equals to NEVD. From this concept map of drift velocity, you can summarize all the details which we have studied in the drift velocity, means its definition, its SI unit, then its formula with the electric field and relaxation time tau, and the relation with the current I is equals to NEAVD, and by putting the value of VD in this equation you got NE square A tau E upon ME. In terms of mobility, now Ohm's law can also be deducted by using this drift velocity relation, and students note that in board exams this question is asked many times. So by using third equation, VD is equals to EE upon M into tau, and you also know that the electric field relation and the potential relation E is equals to V upon the distance across the ends, and here the length L is the distance, so E is equals to V by L. So by putting the value of E in the VD equation, you got VD is equals to EV upon ML into tau. Also you know that I is equals to NEAVD. By putting the value of VD from the above equation in this current equation, you get equation 7, and from equation 7, V by I will be equals to M into L upon NE square A into tau, and you know that this one is constant and that constant is equals to R. So if we compare Ohm's law, then V is equals to IR and the value of R will be ML upon NE square A into tau, right? We will continue this topic in the next video. Thank you.